Hi, good morning. Welcome to engineering drawing classes. And here I am Dr. Vasu. I have given all the earlier lectures through PPT, but I prefer this particular topic on orthographic projections in person on board. Why? Because it needs a special explanation and I need an object to explain this particularly. So here we are going to see the orthographic projections and what is meant by orthographic. Ortho means perpendicular. So before going to that, let us see one example. Suppose I have one object. I have an object here like this and I want to represent this. I want to draw the figure of it. So for this, we can do, when you see this particular object in this direction, we see it as a rectangle. Okay? So how to get it? That is for this, we start with, let's take a candle. I take the object here and I put the candle in front of it, and what happens? I have taken a vertical screen here, right? A screen. When you take the candle here, the light rays coming from this, they fall on the object, and how will be the shadow formed on the screen here? Yes, you guessed it right. You get a rectangle, but a bigger one, bigger than this. How? Why? Because the light rays coming from this candle are falling like this at an angle to the object, and they form a bigger rectangle like this. We don't want it. So let's move this candle far away from the object. Move it further. What happens? The size of the shadow decreases, right? Let's say the candle has moved to, the light source is moved to infinite distance. What happens? Will it disappear? No. It appears. We get a shadow of the same size, a rectangle of same size. Why? Because the light rays coming from an infinite source, our sun, are all parallel to each other and they fall perpendicular to this object. When they fall perpendicular to this object, because they are falling perpendicular to this object, we call it as orthographic, perpendicular. And all these light rays coming from this, they form on a shadow here on the screen, right? Now, we call it as a shadow, or instead of it, we call it as a projection, right? Like a projection means in the cinema theaters you would have seen the light rays coming from the cabin and falling on the screen. Like this, the light rays coming from the light source, they fall on the object and they form an image. That image we are calling it as a projection. Because we get a image here like this. For this particular object, we get a rectangle like this. This rectangle is of the same shape and size, and we are getting the length of the object and width of the object, right? 2 dimensions. But this is a 3-dimensional object. Can you see the 3rd dimension? No. Why? Because the 3rd dimension is somewhere else. We cannot see it in this view. Now, how to get it? Let us do one more thing. I have taken a horizontal screen here on the floor, and I have taken the light source on the top, right? The light rays coming from the top, they fall on the object here and they form an image. How will be that image? Again, you get a rectangle, right? Like this, and this rectangle is, so what is happening? You are able to see the thickness of this object and length of the object. But that means when you are actually, we don't have a light source, or we just imagine the object and its shadow or the image or the projection. So we are getting two projections. This projection is obtained when the object is looked from the front side. This is when you are looking from the top. So I call this one as front view, and this one as top view. Front view also is called as elevation, and top view is also called as a plan. So to get all the three dimensions of an object, we need two projections. So for this, you have actually imagined a horizontal screen and a vertical screen here. We don't have any screens and no shadows. Actually, we imagine how the object looks like when I am looking at it from the front, from the top, right? For this, we take an object here like this. We take two plane surfaces. One is a vertical one, another horizontal, right? These two planes are just imaginary planes, only for our purpose. We consider them as transparent, right? And they are just imaginary planes. Here, a vertical plane and a horizontal plane, both are intersecting. What is the intersection of these two planes? Any two planes? A line. Intersection of two planes is a line. So here, the line is horizontal and we indicate it as the XY line. X, small x and y, right? So the orthographic projections which we are going to see them are the ortho in the sense the light rays coming and falling on the object perpendicular to it and getting the image on these screens, on these planes, reference planes. So that's why these are orthographic projections. Next, suppose you have taken two planes here. These two planes are actually movable and actually this horizontal plane, this is only one plane. As a plane, it can be rotated. And it is forming actually four parts. This is dividing the space here into four parts. These parts are named as, just when you are looking at it, you get one idea, isn't it? That is nothing but it looks like your graph sheet with x-axis and y-axis. This x-axis horizontal and y-axis here. This screen is, this space is divided into four parts. Let's name it. How? We call this part as the first quadrant in your graph sheet. Second, third, fourth. Like that, we divide this space into four parts called quadrants. Their names are 1, 2, 3, 4. Right. Now, we take the objects in different positions of these planes and we indicate their projections, how they look like in the front view as well as in the top view. Now coming to this, suppose we have an object in here in the first quadrant. It is said to be in front of VP. It may be here or here. The object, when it is here, it is in front of. If it is here, it is said to be back, behind VP. For horizontal plane, it is either here or here. It is said to be above the horizontal plane, and here it is said to be below the horizontal plane, like this. Now, we are actually going, we draw the projections of different objects, starting from lines, planes and all. Before we start with a single one-dimensional line, let us start with a no-dimensional object. That is nothing but a point. So let us see the projections of points. The projections of points, suppose I take a point A. We have to specify where that point is. The point is, suppose the point is here. It is said to be in the first quadrant, in front of VP, above HV. Okay? Now the point is 30 mm in front of VP, 40 mm above HV. This is the position of the point. Now, point A is 30 mm in front of VP, 40 mm above HV. We draw the projections of it. How? When you see this point in the front view, the point appears at a height of 40 mm because this is 40. At a distance of 40 mm, you get the projection here. So we indicate that it is a point, just simple point like this. And we have to, at what height? 40 mm, right? At a height of 40 mm, we got this point. This is, its name is A, but you have to say it is the front view of the point called A. That can be simply written as A dash. If you write a dash, that indicates this is the projection of a point called A. It is 40 mm above HV. Now, take the projection of this point in the top view. When you are looking from the top, its projection obtained here on the horizontal plane. Now, rotate this horizontal plane like this. We rotate the horizontal plane like this as a single plane. How do you rotate? You get a doubt. Suppose, can we rotate in the reverse, other side? No. When you look from your left side, right? When you look from your left side, you will be rotating this in the clockwise direction only for you, clockwise direction. So this horizontal plane coincides with the vertical plane. Now what happens? The projection you got here at a distance of 30 mm in front of VP is obtained here below the reference line. This horizontal line is a reference line. Below this reference line, we get it at a distance of 30 mm, right? So, on the same, this line is called projector, right? Projector in the sense, it's a light ray coming from the light source, like that. It is perpendicular to the reference line always. And we are not moving the object. That's why the projection of this point should be on the same line here, perpendicular to the reference line, at a distance of 30 mm. So this is the top view of that point. So the top view is A. The point is called A. Simply the top view is indicated with a small letter, front view is indicated with a small letter and a dash. That is the only difference. So we got the orthographic projections of the point called A here. Now, suppose the point, another point, I take B. The point B is here. Where? In the third quadrant. How? Some 40 mm behind, let's take 20 mm behind VP, okay? 20 mm behind VP and 50 mm below HV. 50 mm below HV. 20 mm behind VP. The point B is 50 mm below HV, 20 mm behind VP. So, the point is here, 20 mm below HP, behind VP, 50 mm below HP. This is the point. The point is here. Now, I want its projections. When you look at it in the front view, the point, the projection, because this is just imaginary plane, you can just imagine transparency. The projection obtained here for this point, 50 mm below, is here on the VP. Okay, and one more thing, this plane is called vertical plane and this plane is called horizontal plane. Simply, you may call this one as vertical plane as VP and the horizontal plane as HP. So the projection of this point is obtained on the VP, vertical plane, at 50 mm below HP. So 50 mm below HP, we draw a point. This is the projector and 50 mm here. This point is called B. B or B dash? B dash, because you are getting it in the front view. So it is B dash. Next, its projection is obtained 20 mm behind VP here. So rotate, the projection is obtained on the top. When you are looking in the top, its projection obtained here at a distance of 20 mm on the horizontal plane from VP. Rotate this, and this top view is coming here above the reference line. Above the reference line at a height of 20 mm. So draw a line here at a height of 20 mm, and this is B. Simply B, because it is the top view. Got it? Now see the difference. Here this point is in the first quadrant, point B is in the second quadrant. Sorry, third quadrant. What is the difference? Do you observe the difference? Here the front view is obtained above the reference line. Here it is below the reference line. Top view, here it is below, here it is above. So when the point is in the first quadrant, the projections are called first angle projections. This is called first angle projections. When the object is in the third quadrant, the projections obtained are called third angle projections. Earlier we used to follow third angle projections, but nowadays the standard is first angle projections only. We are following first angle projections. But for the time being, in the sense, for some topics like projections of points and lines, they can be given in any quadrant. So in any quadrant it can be given, but later on we follow only the first angle projections. Means front view is above the reference line, top view is below the reference line. Clear? Now, suppose I have taken another point called C. A point C in the second quadrant will take. Second quadrant in the sense, behind VP, 20 mm behind VP and 30 mm above HP. That is here, second quadrant. 20 mm behind VP, 30 mm above HP. 30 mm above HP, like this. So, first of all, let's draw its front view. Front view is 30 mm above HP. So the projection obtained here on VP is 30 mm above HP. So at a height of 30 mm, draw the reference line, a thin horizontal line indicated with XY, and 30 mm height, you draw a point, mark a point, that is called a C dash. Because it is the front view. Height 30 mm. 30 mm above HP. Now, the point is 20 mm behind VP. 20 mm behind VP. So the projection when it is obtained in that when looking from the top, it's the projection obtained on the horizontal plane. So rotate this and get the top view. Where is it? 20 mm above the horizontal reference line. So 20 mm above the reference line, on the same projector, you mark this point. This is 20, and here it is the top view. So mark it as C, the top. Do you observe the difference with the earlier ones? Both the projections are obtained on either side of the reference line earlier, Now they both are on the same side. Let's take a point in the fourth quadrant. Fourth quadrant is, say, point D. Let's take the point D, 40 mm below HP and 50 mm in front of VP. In front of VP. That is 40 mm below HP here and 50 mm in front of VP. This is the point D. Now I want its projections. Look at it in the front view. In the front view, it is how much? 40 mm below HP, below the reference line. I get the projection here on the vertical plane at a distance of 40 mm. I get this projection here. So this is at a distance of 40 mm from the reference line. Okay. D dash front view is obtained. Okay. Now 50 mm in front of VP. This distance is 50 mm. When you see this from the top, at a distance of 50 mm, you see the projection here on the horizontal plane. Rotate this entire plane, horizontal plane, like this. Like this. You get the projection here 50 mm below the reference line on the same projector. On the same projector, from the reference line at a distance of 50 mm, 50 mm, you get the top view. So because it is the top view, mark it as D. So if you observe this point in the second quadrant, point in the fourth quadrant, in both the cases, both the projections are on one side of the reference line. So there is every possibility, if you try to draw the projections of a solid, a three-dimensional object like this. When you draw it on the projections, one may be overlapping on the other. We don't get a clear picture, right? We cannot get all the three dimensions clearly. That's why there is no such second angle projections and fourth angle projections. We have either first angle or third angle projections only, right? So suppose we have a point on both the planes, means it should be on HP as well as VP. How? It must be on the reference line. When it is on the reference line, how to indicate? Suppose the point is E. The point is E on both the planes on the reference line. So its front view is on the reference line as well as its top view is also on the reference line. So indicate both the points on the same projections on the reference line itself. So like this we get the orthographic projections of points. Next let us see the other one-dimensional, two-dimensional, like that. Okay, hope you understand this topic very well, orthographic projections as well as projections of points. So if you have any queries or any doubts or suggestions, please do send through comments below, right? Do comment and do subscribe to the channel so that it will be motivating for me to do more videos like